Okay, we are going to start. Okay, welcome everyone to grade 7 8 Olympic Math. This is our first class, and hopefully, we'll have a very good year together. So, I'm going to introduce myself for those of you who do not know me yet. So, my name is Eric Xiao, and I am a grade 12 student who goes to Sir John Macdonald Secondary School. And I have lots of subject interests, but mostly I'm interested in mathematics. I also love computer science, physics, and music too. And some of the hobbies that I do um, are that I love to code. I sometimes solve math problems in my free time. I also love playing video games, watching YouTube videos, surfing the web for random stuff, and I like reading science articles and business magazines as well. And what I want to become when I grow up, either like a software engineer, an entrepreneur, or a professor. So that's a little bit about me. And then next we'll move on to like an icebreaker so all of you guys can get to know each other a bit better. So basically, during this icebreaker, you just tell us your name, your grade, which school you come from, and why you signed up for this class or what you want to learn in this class. So are there any volunteers who want to go first? Does anyone want to go first for this icebreaker? Or I'm going to choose and pick. All right, sure, go ahead. Eric. Mhm. Yeah, yeah, yeah. Mm. Right. That was a really good introduction, Eric. Good job. Yeah, I relate with a lot of things you say. Hmm? No, 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 no. Just no, not at all. That's all you have to say. So it's perfect. Thanks, Eric. Does anyone else want to go? Anyone else want to introduce themselves? No, no, it's fine. Um, Otherwise, I'm going to choose and pick. Okay. Um, how about Adela? Can you introduce yourself? Hmm. Hmm. Also unsure. That's okay. We'll try to go through like a bunch of different variety of topics through this year. So hope your expectations are met. We'll try to not repeat any of the stuff we learned last year as well. So yeah, that'll be good. All right. Yeah. What's your question? Instruments. Yeah. So I used to play the piano. I think I stopped in like grade 10 after I finished grade 10 piano exam at Royal Conservatory of Music. And now I play saxophone at the school. So that's my school instrument. Yeah. Yeah. But it's not like a big hobby of mine right now because I'm really busy with like math and computer science stuff right now. So yeah. Right. How about Bob Zhao? Would you like to go next? Mhm. Mm. Typical. Just math. Okay. Like any specific topics in mind or no? General math. Okay. That sounds cool. Thanks, Bob. All right. Chengao, would you like to go next? Mm, algebra. That sounds cool. Yeah, I'm playing that algebra stuff for our curriculum. Welcome back, Chengao. Hopefully we'll have a good year together. Next, how about Chenglong? Would you like to go next? Mm, that's great as well. That's fine. Yep. Okay, thanks, Chengle. How about Elaine? Right, that sounds good. Thanks, Elaine. Now, how about Jeffrey Tao? Would you like to go? Mm-hmm. Ooh, cool. Mhm. That's fine. That's fine also. We'll try to go for like various topics and see like what you're most interested in. So, John? Is your name John? That's not that's a joke. Oh, okay, go ahead. Hmm. Hmm. Yeah, it's a really good introduction. We'll try to go through well, not like the like really difficult topics, but like more complex ones than like the one we're about to learn about today. But good introduction. Let's see. How about Jerry Leo? Would you like to go? Mhm. Mhm. Ooh, geometry. It's good. Definitely gonna look up onto that. I know geometry is very difficult to like teach online because like the diagrams and stuff, and it's like hard to like actually draw on like an online whiteboard. But I'm gonna try my best to teach geometry. Good introduction. Next, Jesse. Would you like to go? Is this? No. Would you like? Oh, okay. Wait. Yeah, Jesse. Would you like to go now? Yeah. There you go. Oh, cool. Hmm. That's fine. But good introduction. You said your sister Joy's here as well? No, that's all right. Let's see. I'll go straight to Kayla. Kayla, would you like to go? Right. Yep. Good introduction. I also used to go to Lorewood. It was a pretty good school. Next, Kevin Park. Would you like to go? Algebra. Cool. And what school you go to? And a stapler. Very nice. Thanks, Kevin. Next, how about Patrick Tai? Would you like to go? Mm-hmm. A little bit of everything. Yeah, very good. Just gonna make you well-rounded. And last but not least, Wei Ming Zhang. Would you like to go? Wei Ming, would you like to introduce yourself? All right, I guess not. That's okay. All right, thanks for the introductions, everyone. Hopefully, you all got to know each other better. Hopefully, we'll have a good year. Now, let's go on to the why you've came here today, the actual topic. Today, we're going to learn about number theory, and it's like a really huge topic, but we're going to split into small chunks. So before we go into number theory, we're going go through some definitions. These are most likely a review for most of you, but if it's not, I'll also try to explain them clearly for you guys. So the first definition you need to know is an integer. An integer is a number that can be written without decimals or fractions. And these can be positive integers. Integers can be positive, they can also be negative, or they can be the number 0 as well. So examples of integers are like 1, 2, -1, -2, and so on. That's what an integer is. Now let's go to a more specific type of integer. This is called a whole number. A whole number is a non-negative integer. So an integer that's not negative. It's obvious. But examples are 0, 1, and 2, and all the way up there. And those are whole numbers. And then the third definition you need to know is a variable. So variable is a symbol, but usually we use a letter like X, Y, or Z. And we use that to represent a number that we don't know. So that's what a variable is. So are there any questions about these definitions? I think that's good. We can move on. Oops, I skipped a slide. So I'm going to introduce number theory to you guys. Number theory is the study of integers, which are numbers without decimals or fractions again. And these involve questions that range from like simple arithmetic questions, like for addition, subtraction, multiplication, division, to difficult word problems like how many integer solutions are there to the equation x cubed plus y cubed equals z cubed. You guys don't need to know how to like solve that. The answer is 0 if you want to know, but it's a really difficult proof, so I'm gonna skip that. And here's a famous quote from Gauss. Gauss was a famous mathematician. I think it was like the 1800s or something, but he was a very famous mathematician that like shaped a lot of like these math topics that we usually teach today in Olympic math. And so here's a famous quote from him. Mathematics is the queen of the sciences, and number theory is the queen of mathematics. So as you can tell, number theory is like a really huge branch of mathematics. And now let's move on. First, we're going to talk about a subtopic of number theory called divisibility. And this is basically you're trying to find if one integer is divisible by another. So here, for example, we have 10 is divisible by 5, right? 10 divided by 5 equals 2. But 10 is not divisible by 4. 10 divided by 4 would give you an integer or a fraction. Now let's express divisibility in mathematical terms. So now we're going to use variables. So say if variables a and b are integers, then b divides a, So like this notation right here, we have b dash a. It just means b divides a, or a is divisible by b. So this happens if and only if there is an integer c, so c is another variable, such that b times c equals a. So that's the definition of divisibility. Are there any questions about this? Oh, think of something in the chat. Okay, no. Think we're good with divisibility. Let's move on. Here's some common divisibility rules. So if you're dividing by a number, there's a rule that tells you if the number is divisible by that number. So let's go through them one by one. These are, never mind. So say we're looking at divisibility rule for 2. So you're trying to find if a number is divisible by 2. You should check if a number is even. So when it means even, the number ends in 2, 4, 6, 8, or 0. So pretty self-explanatory. How about divisibility by 3? So if a number is divisible by 3, the sum of its digits is divisible by 3 as well. I can give an example, say like 123. So 123, the sum of its digits is 1 plus 2 plus 3, which is 6, and 6 is obviously divisible by 3. So therefore, 123 is divisible by 3. Now, divisibility by 4. You take the last 2 digits and make that a number by itself, and if that number is divisible by 4, then the entire number is divisible by 4. So say I took the number 104. The last 2 digits would be 0, 4, which is just 4, and obviously 4 is divisible by 4, so 104 is divisible by 4. Right, the next, divisibility by 5. This is pretty simple. You see if a number ends in a 5 or a 0. That's all. Now, divisibility by 6. You have to see if the number is divisible by 2 and 3. So it can't be just 1. Like if it's just divisible by 2 but not 3, therefore it's not divisible by 6. It has to be 2, divisible by both 2 and 3. So you use these rules for 2 and 3 to determine if it's divisible by 6. We're going to skip divisibility by 7 because it's actually pretty complex. But you guys can like search it up on your own if you want, and you'll figure out what it is. I'm going to go to divisibility by 8. So for this, we have to see if the last 3 digits is a number that is divisible by 8. So say I took the number 1,800. So the last 3 digits would be 800, which is 800, and 800 is divisible by 8. So therefore, 1,800 will be divisible by 8 as well. Now let's look at divisibility by 9. This is very similar to the divisibility by 3 rule, where you just take the sum of the digits, but now you figure out if that's divisible by 9 as well. And lastly, divisibility by 10. It's similar to divisibility by 5, except that you have to see if the number ends in 0. Are there any questions about this? No questions? Guess we can move on to some problems. So here are 5 questions for each of the following. First, determine if A, so A right here, is divisible by B. And if A is divisible by B, find the value of C. So C would be an integer such that B times C equals A. If it's not divisible, then you don't have to find value of C. So I'll give you guys a moment to solve these questions. Should be fairly straightforward. I'm going to wait a couple more seconds. All right, I'm going to take. Now let's look through each of the questions one by one. So does anyone have an answer for question number 1? Yep. So what's the answer? Yeah, it's not divisible, right? 4 divided by 3. 4 is not divisible by 3. And you don't have to find the value of c. So that's number 1. How about question number 2? So c is 8. And we know that 16 is divisible by 2. 16 divided by 2 is equal to 8. So c is 8. How about question number 3? I'd like someone else to answer this. So question number 3 is 1,270 divisible by negative 10. Perfect. Yeah. So this is a kind of a trick question, but we can divide positive and negative numbers together. But then when you divide positive by negative, you would get a negative answer. But here, 1,270 is divisible by negative 10 because they both end in 0. And so when you divide them, you get negative 127. So C is negative 127. So that's question 3. How about question 4? Yeah, C is positive 90. So we know that negative 90 is divisible by negative 1. Actually, all of the integers are divisible by 1 and negative 1, actually. And when you divide them, you basically get rid of the negative here. And so you're just left with C is equal to 90. Okay, how about question 5? Not divisible, right? So remember the divisibility rule of for 9 is you take sum of digits and figure out if that's divisible by 9. So for 121, it's 1 plus 2 plus 1, which is 4. 4 is obviously not divisible by 9. So 121 is not divisible by 9. And we don't have to find the value of C. Are there any questions about these problems? Anything confused about? Or like questions about like the previous topic stuff we covered? I think we're good. Let's move on. Oh, I keep skipping slides for some reason. We're going to talk about prime numbers. So prime numbers are a special type of whole number that has exactly 2 whole number factors. So factors are numbers that divide evenly in a number. So for example, let's look at the prime factor 2. 2 has factors 1 and 2. So 1 and 2 also have to, so the factors also have to be whole numbers. They can't be negative. And so since though these are 2 factors, therefore 2 is a prime number. So now if a whole number is divisible by more than 2 whole number factors, you would not call it a prime number anymore. It's called a composite number. So composite numbers have 3 or more factors, whole number factors. And cool fact, 1 is the only whole number with only one whole number factor. It's just 1. So therefore, it wouldn't be classified as a prime number or a composite number. It's neither. Are there any questions about this? No questions. We can move on. Now let's look at a term called prime factorization. It's a very useful technique we'll use to solve lots of problems. So all whole numbers that are larger than 1 can be expressed as the product of 1 or more prime numbers. I think there's actually a proof that actually proves this statement, but we won't go over it today. So for example, if we want to look at the prime factorization of the number 10, we're going to look at its prime factors. So as factors are 1, 2, 5, and 10. Those are the only factors that 10 has. The only prime numbers in those factors are 2 and 5. So we can express 10 as 2 times 5, where 2 and 5 are both prime. This is a useful method to find all the factors of a number, actually, because you can combine these prime number factors, so you can multiply those factors with themselves, and you get another factor of the larger number. I'll go over an example of that later. So say if the prime factorization of a number contains multiple of the same factor, you combine the factors into a power. So we haven't seen a power before. It basically looks like a number and then with like a smaller number at the right. It's just to show like a product of the number by itself. So for example, when you look at the number 20, the prime factorization for 20 is 2 times 2 times 5. These are all prime numbers. And you see that there are two 2's right here. So we can combine them into a power, and we can rewrite this as 2 to the exponent 2, or 2 squared. So 2 squared times 5 equals 20. Are there any questions about this? You have no questions? That's good. Let's move on. So we're going to use this technique to prime factorize large numbers. It's called using a tree, actually. And I will show you how it actually works. So do you guys see this whiteboard that I have right here? Do you guys see this whiteboard? Tell me like yes or no. Yeah, you see a whiteboard? Okay, good. So I'm going to demonstrate the tree technique on this whiteboard right here. I'm going to pick a random number. Let's say 100. Right. And from 100, we're going to draw two lines that go left and right, like go down, left and right. And now we're going to factor this one. We're going to keep factoring this until we only get prime number factors. That's basically how the tree technique works. So can someone tell me a prime factor of 100? Like just any factor. 2, perfect. So we can write 2 on the left. It doesn't really matter where you write it, but I choose prefer on the left side first. And 2 times what is equal to 100? Someone tell me that. 50, perfect. Okay. So 2 is a prime factor. We don't have to like draw a subtree off the 2. So we don't have to draw lines here for the 2. But we notice that 50 is a composite number. It definitely has more than 2 factors. So now we're going to factor off 50. Someone tell me a prime factor of 50. We can use 25, but it's not a prime factor. Well, 2, yeah. 2 times 25 is equal to 50, actually. So we can write 2 and 25 for the branches. And now we can branch off 25. What are the factors of 25? There aren't that many. 5. So 5 it's a prime factor. What's the other? And 5, yeah, 5 times 5. So now, since both of these are prime numbers, we're basically finished the tree technique. So we don't need to go down any further. And also we have to combine these 2's together with the 5's right here to complete the prime factorization of 100. So we can just write these numbers down below. So 2 times 2, sorry for my messy writing right here, but hopefully it's clear. So you take all of the prime factors that you got from the tree and you just combine them for the prime factorization. So 2 times 2 times 5 times 5. That's the prime factorization of 100. And if you want to condense this, you can combine the 2's and the 5's into a power. So we have 2 squared times 5 squared. And that's your prime factorization of 100. Are there any questions about this technique? No questions? I think that's good. It's great that you guys understand all of these concepts. So let's move on to some problems. So try to prime factorize each of the following numbers. I'll give you guys a few minutes. Wait one more minute. Okay, I think we're going to take up the questions now. Can someone tell me the answer for question 1? 2 times 7. Good. I'll try to go through each of the solutions too on the whiteboard right here. So we haven't gone there, but yeah, that seems like the correct answer. We'll go over that soon. It's okay. It's okay. Let's see. I'm going to try to make a new canvas, new drawing. There we go. Okay. So let's go over the solution for 14 or question 1. So 14, the only prime factors it has are 2 and 7. Or those are like the only factors it has as well, other than 1 and 14. So we have 2 right here, and we could write 7 on the right side. And since these are both prime numbers, we have finished, we just finished this tree right here. So the prime factorization of 14 is just 2 times 7. That's all. Okay. And we actually gone over the second question as well. So 30. Someone said 2 times 3 times 5. And so here, let's use 2 as one of the prime factors. Yes, 30 is divisible by 2. And 30 divided by 2 is equal to 15. So we don't have to branch off the 2. Whoops. It looks like 12. Sorry. So now we don't have to branch off the 2, but 15 is a composite number. So now we have to branch off the 15. 15 is divisible by 5. You could have also chosen 3, but it doesn't matter because 3 times 5 is equal to 15. So let's choose 5. And 5 and 3 are both prime numbers. So just like that. And then we just take our prime factors and combine them together. And then we have 2 times 3 times 5. And that's the prime factorization for 30. Right. Someone tell me the answer for question 3. So the answer for question 3. You be careful there. Don't 1 is not prime and it's not composite either. So you can't put 1 in your factors. So you just leave it as 19 because it's okay. Don't be afraid to make mistakes. Like it's fine if you make mistakes as long as you learn from them, of course. But yeah, 19 here is a prime number by itself. So the prime factorization of 19 is just 19. That's all you have to write down. How about question 4? Does anyone have an answer for that? Yeah, go ahead. No worries if the answer is wrong. Oh, sure. Does anyone else want to pitch in? Yeah, it's 7. Yeah, I can go over this actually right here. So 128. Sorry, the 8 doesn't look too good, but whatever. Um, so it's obvious that 2 is one of its prime factors because it's an even number. So we can do that. And 2 times what is equal to 128? Does anyone know? Yeah, 64. So now we leave 2 where it is, but now I have to branch off to 64. 64 is also divisible by 2 because it's even number. And I'll fill out the rest. So 2 times 32 is equal to 64. This is actually going to be a really long tree, actually. Just realized. So now we have to branch off 32. Realize that it's also an even number, just like these two numbers. So we can also use 2 as a prime factor, and 2 times 16, which might not even have space for the other 2's. So let's try our best. 16 is also divisible by 2. That's 16 is just 2 times 8. Um, okay, I think we can do one more. 8 is 2 times 4, so we use 2 as a prime factor again. Okay, I'm going to continue this 4 over here. I know this is whack, but 4 is just 2 times 2. And we finish. So all the 2's are prime factors of 128. And now we have to count how many 2's there are. We're not going to write like all of the 2's. We're going to combine them into a power. So here I have 1, 2, 3, 4, 5, 6, 7. So that's 7 2's. And if you want to combine them, you make 7 as your exponent in the power. So 2 to the exponent 7 would be your answer for question 4. So the prime factorization of 128 is 2 to the 7. Are there any questions? No questions. All right, that's fine. Let's move on to some other terms. So you probably heard this one. It's called the greatest common factor and should be pretty self-explanatory. It's just the largest factor that 2 or more numbers share. And the trick to get the greatest common factor is to first get the prime factorization of all the numbers and then find which prime factors they have in common. So for example, say I want to find the greatest common factor. We usually refer to it in the short form of GCF. So the GCF of 32 and 12, first we prime factorize these two numbers. If you prime factorize 32, you get 2 to the exponent 5. For 12, it's 2 squared times 3. And so the GCF for both of these, so we look at like which factors that they share. We see that they share these 2's right here, but we have to take the smallest number of 2's. We can't take 2 to the 5, otherwise 12 wouldn't be divisible by 2 to the 5. So we would take 2 to the exponent 2, 2 squared, as our greatest common factor, and 2 squared is equal to 4. And you can double check yourself that 32 and 12 are both divisible by 4, and it's the greatest factor. So are there any questions about this? Mhm. You take the smallest power. I already said that. Because like if you take the largest power, then it might not be a factor of the other number, right? So say we took 2 to the 5. Well, 2 to the 5 is 32, obviously. 12 is not divisible by 32, so we can't do that. So we have to take 2 to the power of 2. Are there any other questions? All right, that's good. Let's move on. Just solve this one problem. Find the greatest common factor of 96 and 64. I'll give you guys a few minutes to solve that. Let me submit. Just a few more seconds. All right, I think we're going to take this up now. Does anyone have an answer for this? It's not 8. Go bigger. Yeah, 32 is correct. All right, we're going to take this question up. Let me erase these. Hopefully, it doesn't take too long. I don't think I can increase the eraser size, so that's a bit tedious. But yeah, we're going to continue on this whiteboard because 64 is one of the numbers in the question, and we can the prime factorization 64 is actually over here. We just remove one of the twos. This one, wait, which black dot? Oh, wait, okay, now let's try it. Okay, that helps so much. Thanks. This is my first time actually using Google Canvas, so I was trying to familiarize myself with it. Okay, so we're continuing off because we have prime factorization 64 over here. So we just keep taking the prime factors of 2 and decreasing like the number on the right until you get to 2 times 2. And actually, 64 has one less prime factor of 2 than 128. And if you count all the 2's, so like start from here, 1, 2, 3, 4, 5, 6. There are 6 2's. So prime factorization of 64 is 2 to the exponent 6. Now, the other number is 96, and we're going to have to prime factorize that individually. So can someone give me a prime factor of 96? What's a prime factor of 96? 3. Yeah, 3 is one of them. Because look, 9 plus 6 is 15. 15 is divisible by 3. So that's good. All right, and 96 divided by 3, that should give you 32. Right. Now, actually, I won't continue over here. You notice that 32 is also in the prime factorization tree of 64. So you see at 32. So ignore the stuff from here. Ignore that stuff. Let's look about over here. So 32, you just also keep dividing by 2 until you get 2 times 2. and there's actually 5 twos. So 1, 2, 3, 4, 5. So we're just gonna we're gonna skip the prime factorization tree over here. We're just gonna use this one. So actually, we're just gonna write 2 to the exponent of 5 right here. And we also remember we also have to carry the 3 down there as well. So prime factorization of 96 would be 3 times 2 to the exponent of 5. And so now we have to compare this with prime factorization of 64, which is 2 to the 6. And you see that they both share prime factor of 2, but remember that we have to take the smallest power of 2. And this is the smallest power right here, 2 to the 5. So therefore, the greatest common factor is 2 to the 5, which is 32. You probably already noticed that because they both 64 and 96 already share 32 in their factorization tree. Well, that's the answer. Does anyone have any questions? No questions? Okay, think we're good for that question. That problem. Now let's go on to another term. Probably heard of this already. It's called the lowest common multiple. So first, let's define what a multiple is. Multiple is just a number that can be factored by another number. So it's kind of like the opposite of factor. Instead, you take a multiple is like the larger number. So for instance, 15 is a multiple of 5. 15 divided by 5 is just 3. Now, what's the lowest common multiple? Well, the short form of it, we usually refer to it the short form, which is LCM. It's just the smallest common multiple that is shared between multiple numbers. And the trick for this is actually slightly more difficult than greatest common factor. So you do get the prime factorization of all the numbers, but then you have to write down. So first, write down the factors that are repeated in all of them only once, and then you write down the factors that only appear in one of the numbers. So I'll give you an example of what that looks like. So here we're trying to find the lowest common multiple of 10 and 15. Here, 10 is equal to 2 times 5, so that's the prime factorization of 10. Prime factorization of 15 is 3 times 5. So this is basically the opposite of greatest common factor. Now we have to take the factors that they don't share at all, and also for the factors that they do share, we have to take the largest. Actually, you take the largest power of them. I can't show it right here. Actually, I'll change the numbers around just to make it more clear. So say I did let's see 75. Let's try 75. So this would be 3 times 5 squared. And so instead, you don't take the smallest power, you would take the largest power, which is 5 squared. So let's do that. 2 times 3 times 5 squared. That should give you 150. Go back. Okay, yeah, this is a better example of like how it's the opposite of greatest common factor. So here in the prime factorizations, they don't 10 only has a 2, and 75 is the only one that has a 3. So I have to put both those in the lowest common multiple product. So 2 times 3, you see 2 is from 10, 3 is from 15. And for here, you see that they both have a 5, but we have to take the largest power of 5 instead of smallest from the greatest common factor. For lowest common multiple is largest power. So we multiply by 5 squared then. And if you calculate that, so 2 times 3 times 5 squared, that should give you 150. Are there any questions about this? I think this might be a little bit more confusing than greatest common factor. There are no questions? I think we're good. Okay, now let's go through an LCM problem. So find lowest common multiple of 35 and 25. Give you guys a minute to do that. Okay, I think we're going to take up this question. Does anyone have an answer for this so far? 175. I think that seems correct, but let's double check that actually. So let's prime factorize 35 first. Okay, can someone give me a prime factor of 35? 7. Perfect. So, and what multiplies by 7 to get 35? 5. So 7 times 5 is 35. And these are both prime numbers. Oops, let me erase that line. Yeah, 7 and 5 are both prime numbers, so we can just leave the prime factorization like that. Now let's look at 25. Someone give me the prime factorization of 25. 5 times 5. That's the prime factorization of 25. All right, so now we have to compare these two right here. We see that for 35, it has a 7, which 25 does not. So 7 is going to belong in the LCM. Now we know, and we also know that they both share 5s. But for the lowest common multiple, we have to take the largest power of 5. I should have written this as 5 squared. So largest power of 5 between 5 and 5 squared is obviously 5 squared. So we're going to take the 5 squared, put it over there. And this is the lowest common multiple of 35 and 25. Going to solve this. So that's 7 times 25. And if you solve that, you get 175. And that's your answer. Does anyone have any questions? Whoops. Do I mean to do that? No questions? Okay. I'm going to end this class with a few more problems. So here, find the greatest common factor. Did not mean to put D right there. And the lowest common multiple of 84 and 14. So I'll give you guys a minute to solve that. we're running short on time, so let's just take this up. Let me get a new canvas. Okay, so we're going to prime factorize both 84 and 14 to get GCF and LCM. Let's start with 14. Can someone give me the prime factorization of 14? 7 and 2. Yep. 7 and 2 are both prime numbers. So we're just going to leave it like that. Now let's go to 84. Someone give me a prime factor of 84. Yep, 2 is one of them. Yeah, we can start with 2. 42, perfect. Okay, how about prime factor of 42? 2 and 21, good. Well, 21 is not the constant number, not a prime number. So we can branch off 21. 3 and 7, perfect. And we can end it right there because 3 and 7 are both prime. If we combine this, we have 2 times 2, so 2 squared, times 3, times 7. Okay, and now we have to compare it to and find our GCF and LCM. So first, let's find the greatest common factor. So GCF. Does anyone know the greatest common factor of these two? So like, look at look at the factors that they share. What's the not 84? So I'm looking for greatest common factor that these two share. 14, perfect. Because look, they both share 7, and they both share a 2, just 1, 2. We're not going to take 2 squared, we're going to take 2. So 7 times 2 is your GCF, and that's 14. Okay, how about our lowest common multiple? Does anyone know that? Looking for a multiple, so it has to be larger or equal. 84. Yes, it's 84. So remember how we solve for the LCM? We have to look at the factors that are unique to both of them. We see that this one has a 3. So I'm going to write that first. And now we have to look at the factors that they share. We can only write them down once. So they both share a 7. These are both equal. So we're just going to write down one of them, 3 times 7. We see that they both share 2, but we have to take the largest power of 2, which is here, 2 squared. And that would equal to 84. This is just the prime factorization of 84. So yeah, there you go. Does anyone have any questions? I think we're running short time, so let's move on to this last problem. If x times y is equal to 81, and x and y are both composite, what are the values of x and y? Yes, they can. Yeah, 9 and 9. So running short time, so I'll just explain it over here. So the prime factorization of 81 is 3 to the exponent 4. So 3 multiplied by itself 4 times gives you 81. And you can determine the factors for that. So you get 1. 1 is obviously a factor of 81. 3 is also a factor of 81. And you can also get 9 and 27 and 81 itself. And so if you want to find like the product, like the factors that combine itself to 81, you get 181, 3 and 27, and 9 and 9. Only 9 and 9 work because, so look at 1 and 81. 1 is not composite. It's not prime either, so it doesn't work. For 3 and 27, 3 is a prime number. So